So, today we will discuss stable matching. So, last time we discussed actually, but it was not like correct definition actually, and that is why there was a lot of confusion. So, I will just start it all over again. So, forget about the past definitions and all. Okay. So, this stable matching problem is actually here defined on when you have given two sets of elements and which has equal size. So, basically you can think of as a bipartite graph where you have two sets and both partite set has same cardinality, okay, same size. And what you have given more, for every element in A, you have for every vertex in both the sets, you have some preference list. Okay. So, for every say W in A, there is a preference list or preference order of, there is a preference order with respect order of the elements of B with respect to A, with respect to W. So, basically for every element in A, it has given some preferences to each element of B. Okay. So, it has ranked all, you can say ranked or preferences. So, it has ranked all the elements in B, okay, and similarly every element B also has ranked all the elements of A. Okay. So, we have preference list for all the elements of A and B. So, for every, similarly now for every M in B, there is some list, preference list for elements of A with respect to B. So, we will look at some example. So, this is the given setting, and now what is a stable matching? A stable matching is, so we will say that this is a stable matching. We will say that this matching is a stable matching if, okay, let us see when it is not stable. Okay. So, we will say that this matching is not stable if one of them, so say here this W prefers M prime more than M. Okay. So, what I am saying is that say these are matched, M is matched with W, M prime is matched with W prime, but now I am saying that W prefers M prime more than, so W prefers M prime more than M, and this M prime also prefers W more than its matched partner. So, M prime also for M prime prefers W more than W prime. So, basically if you have such a pair W and M prime such that W prefers M prime more than its partner and W prime also prefers M more than its matched partner, then we will say that this matching is not stable. Okay. So, stable matching is when there does not exist any such pair of M and W such that M prefers W more than its matched partner and W prefers M more than its matched partner. Okay. So, let us
preference lists are not strict, right?
let us assume that this is for a strict preference list.
What are the edges of the graph?
Edges are all possible edges, because complete bipartite, because for every M and for every W we are ranking all the elements of the other part, okay, other set. Okay. So, we will say matching is stable if there exists no MW pair such that M prefers W over its matched partner and W prefers M over its matched partner. Okay, so when there is no such pair, then we will say that our matching is stable. Okay, so let's see some example. So basically now edges doesn't matter because you have given preferences to every element here. Okay, and this is stable matching problem or stable marriage problem, because we can look at it in that way as well, that we have given a set of say women W1, W2, W3, and we have given a set of men. Every woman has some preference list for men, so we can just assign any ranking. So say M2, M1, M3. For this, let's say M3, M2, M1, and for this maybe M2, M1, M3. Oh, this is same as above. M3, M1. Okay. Similarly, for M1, we have some preference. So say W2, W1, W3, W1, W2, W3, and say W2 or say anything 3, 1, 2. Okay. So now we want to find a matching which is stable. So for this, we will talk about Gale-Shapley algorithm. Okay, so which was given by Gale and Shapley. In 1962 for stable matching. Hi Ankit.
Yeah, can you write little bigger?
Oh yeah, sure. Sure, thanks letting me know. Okay. Okay, so for to find a stable matching in this setting, we want to we'll use Gale-Shapley algorithm. So what this algorithm says, so initially all the men and women are free. Okay, so first initialize.
I just had a small doubt.
Yes.
So in the previous setting that we discussed, the preference list was basically on edges, right?
Yes, but here we are assuming that for every person in the other set we have some preference. So actually the original, yes, say.
Now the preference list is not edges, but they are vertices instead, right?
Yeah, but even earlier also, like when we were saying edges, we were looking at the vertices only, right? So for W1,
Right.
yeah, corresponding end point of that edge, other end point of that edge. So earlier also we were ranking those end points, not the edges. But yeah, originally this stable matching problem is also known as stable marriage problem, and in this like standard thing, you have all possible edges. That means for every element you have some preference list for every element in B in the other set. So for every element you have some preference for every other element in the B. So it's not just that you may have fewer edges, but we are considering basically that all possible edges are there. So all possible connections can be built up between A and B. Okay. Yes, this will be a perfect matching because we are taking cardinality of A and B, and we want at the end that every men and women, like every man is married, and so the women also. Okay. This will give us a perfect matching, which is also stable. So first, let's initialize every man and women to be free. Okay. So every man and women are free. Now, what this algorithm does, it looks at some men which is unmarried, okay, which is free. So while we have, there exists some M which is free, and now for every M you have a set of preference list for each woman. So if M is free and M has not proposed to everybody till now, so then that means there is some women which in its preference list whom he can propose to, right. So if M is free and still there is some and there exists some W in its, say, L of M list, preference list, okay, such that M hasn't proposed to W. So till the point we have such element M, what we will do, M is going to propose W. Okay, so what it will do, M proposes to some W. Okay. And any W which he has not proposed yet. So maybe there are two women. So with most preference. Okay, to not some, but to the most preferred women. Okay, M proposes to the most preferred woman by yes, whom he has not proposed yet. So that's why I wrote it in the while loop itself. So you can assume. So maybe during the algorithm, M will propose to some women from its preference list, but she might not be accepted. So it may reject. So once W2 rejects M1, then I cannot propose it again, right? So I have to go to other women. So that's my point, that he has not proposed to some women, and out of those we will look at the most preferred women. M proposes to the most preferred women. Okay. Now what can happen? So there are now two cases. Maybe this W is free. Okay. W is free already. So basically, what this algorithm does, men proposes to women, and now women has the choice whether she wants to accept it or reject it. So what algorithm does, whenever a woman is free and she gets some proposal, she'll accept it, okay, because she is getting some proposal, so it's okay. She does not reject in the first proposal, she always accepts. But then again, maybe some other man proposes to the same women, and this man, for this woman, has more preference than its now matched partner. So it will break off with the current partner and will match with the M2. Okay. So, this is the algorithm, and whenever we have some free men, we will keep doing that. We will look at its list and go to some women which is most preferred and which he has not proposed yet, and he will propose, and then women will decide whether she wants to accept it or not. It is based on whether she is free. If she is free, then she definitely accepts it, and if she is not free and she is matched with some M, then she will see that that proposal, that man which has proposed now, whether it is more preferable than the current like matched partner. So, if it is more preferable for her, then she will break off with the current matching and go with the new proposal. Okay. So, that is the whole idea. So, if W is free, W accepts M and W engages with M. Okay. So, we will change the status from for M, that now it is not free, M is engaged and W is also engaged. Okay. So, we will change the status here that W and M are engaged. Now, as if W is not free. So, W is engaged with some M prime, okay, M prime, and for W, M is more preferable than M prime. So, W was matched with M prime, but this new proposal M is more preferable than M prime. In this case, what W does, W, okay, so let us say W breaks off with M prime and engages with M. Okay. So, now W status was engaged earlier as well, but now it has breaks off with M prime. So, M prime is now free, M prime is free and M is engaged. Okay. So, this like this we can change the status, and otherwise means that W is engaged and with some M prime, and M prime is the more preferable than the current proposal. So, W rejects this M prime, then W rejects M, sorry, W rejects M in that case, and so status would be remain same for every men and women. Okay. That is all. So, that is what we will do. So, till the point we have some men which is who is free, we will go to the its preference list and we will see that who has he has not proposed to which women, and we will take the most preferred women, and then M proposes to that W. And now, if W is free, then W engages with M. If it is not free, W is not free, W is engaged already, then W would decide whether M is most preferable for him or for her or not. Okay. So, let us look at this example, run this algorithm on this for this example. So, first we will start with M1. So, M1 proposes to W2. Okay. So, now because W2 is free, so she will say yes and they will match. Now, we will go to M2. Now, M2 proposes to W1. Now, W1 is also free, so they will match together. Oh, I have given very wrong kind of list because they are just straightforward matching. Like, okay, let us change it to W1 and this is W3. Oh, okay. Now, M3 will go to W1 and proposes to W1. Now, here M3 proposes to W1. Now, for W1 is already engaged with M2. So, we will look at its preference list, and now W1 is already matched with its most preferred men, right. So, she will not break off, she will reject M3. So, she has rejected M3. Now, M3 will go to W3, and so because W3 is free, so they will make an edge. Maybe I should go to W2 first. Okay, let's change it. Say W2 and then W3. Okay, what if M3 has W2 is more preferable for M3? Then it will go to W2 and it proposes, and now W2 is matched with M1 and M3 is proposing W2. Now, in its preference list, M3 has like better rank than M1, right. So, what W2 will do? She will breaks off with M1 and match with M3. Okay. Now, M1 is free. In this step, M1 gets free. So, we will go to M1 and okay, W2 has rejected M1 now. So, we will go to W1. So, now M1 goes to W1, and let us see what W1 says. So, because in the preference list M1 comes after M2, M2 is the current matched partner of W1. So, W1 rejects M1. Again W1 also rejects M1 because she is already matched with most preferred partner. So, W1 also rejected him. So, now M1 goes to W3, and now because W3 is free, so W3 accepts. Okay, so this is a matching. So, this one we good. So, at the end we got this matching. Okay. Okay, so to now to talk about the correctness of the algorithm. So, first of all see whether this algorithm terminates or not, right. So, when this will terminate, because we are adding new matching, we are breaking off, adding new edges. So, we want to make sure that it terminates. Yes, exactly. So, this in the worst case, this algorithm will take n square steps. Why n square steps? So, every man is proposing to somebody. In the worst case, maybe he is rejected by every women in its preference list, but except like last one, and he gets matched with the last one. So, maybe he has to go through every woman to propose. Okay. So, in the worst case. So, that is why, and we are saying if the number of men and women we have like n, so 2n. So, in that case it will be n square. Okay. Okay. So, that means algorithm will terminate in at most n square steps. Okay. So, let us talk about its correctness. So, for correctness we want to prove two things. One thing is that at the end of the algorithm every man and every woman are married, okay? They are matched. So, every men and women are matched This is our claim 1. And second thing is, what else we need to prove? It is stable. Okay. The algorithm gives a stable matching. Okay. These are 2 claims. Okay. So how we will prove that every men and women are matched?
Every men will be matched because if they are not matched, the algorithm will not terminate. But we have proved that the algorithm will terminate.
Yeah, basically every woman is matched because every women we need to show that every woman gets at least one proposal, because once it gets some proposal, it will accept. So W will be definitely matched. Okay. What about any M, any men? Because maybe you'll go to every person.
Can you repeat what you said?
For W, for women, what we said, that if W is free and if it gets any proposal, she'll accept, right? So in able to, like, if W is not matched, that means she has not got any proposal. But for men it is not the same, right? He may propose to everyone and everyone might have rejected him. So that we need to argue. Okay.
No, if everyone has rejected them, then that person will be free.
Yes.
So if they are free, then it will be an infinite loop, but it cannot be an infinite loop because.
But M is free and there is no W in its preference list, which he has not proposed yet. Then it will not go into the loop, right?
If he has proposed and been rejected, the woman is matched already. Matching can be a size
Matching can be?
at most size n.
Yes, exactly. That is the point. If there is some M unmatched, what does it mean? Because according to the algorithm, if M is free and there is any woman which he has not proposed yet, then he will go to propose her. So that means if at the final step M is free, that means he has proposed to every woman and everyone rejected him, right? Now because M is unmatched, so because number of women and men are same, right? So there must be some women which is also unmatched, which is also free. But why this woman is free? Because so that means we will see that, okay, M1 this M1, because M1 is free. So M1 has proposed to W, say W3. So M1 has proposed to W3 or not. Okay, if it has not proposed, then why, according to the algorithm, M should have proposed, right? So that means M1 has proposed W3 as well, and W3 rejected M1. But in which case W3 would have rejected M1? When she is already engaged with somebody who is more preferable than him. But we are saying that W is also unmatched. So that is the contradiction. Okay. So we will prove this by contradiction. We will say, okay, so let there exist some men which is unmatched, and unmatched means that he has asked everybody, he has proposed everybody in his list, and everybody has rejected him, right? Now look at the women which is unmatched, which exist because of the same cardinality of both the sets. So we will look at the unmatched women. We will say, okay, whether M1 proposed to her or not. So like, of course he has proposed, otherwise he should have proposed by the algorithm. So he has proposed and they are not matched, that means W3 has rejected M1, right? And the reason for the rejection is the only thing that W3 is already matched with somebody which is more preferable for her, and which contradicts the fact that W3 was like unmatched. Okay. So, should I write? This is okay, like this is easy. Okay. So, every men and women are matched. Okay, what about second? Please ask if you have any doubts. Is it okay? Claim 1, is it clear that why they are matched at the end of the algorithm?
Yes.
Okay. Okay, for claim 2, we will prove that algorithm gives a stable matching. So, suppose there is some pair M and W which is not stable, We have MW pair which is not stable. What does it mean? That this is my M and this is my W. This is a pair which is not stable, that means W is matched with some M prime, M is matched with some W prime, and W prefers M more than M prime, and M prefers W more than W prime. Okay. So, MW is not stable means this thing. Okay. Okay. So, what will say now? So, yeah. So, if MW is not stable, so but look at the algorithm. M is matched with W prime, but W is more preferable for M. So, what does it mean?
M has already proposed to W, W rejected.
Yes. So, by the algorithm M must have proposed to W first, because W is more preferable than W prime, and because it is not matched with her, that means W rejected M, right. So, by the algorithm we will say M proposed W first and W rejected M. Okay, W rejected M. What does it mean? If W rejected M,
W has more preferred partner.
yes. So, that means the preference for W, preference for M is less than its current partner, right, or not this partner, but something else. But yeah, M prime to hoga, because even if this was something else, like maybe on some step W was matched with somebody else, M double prime, and it was matched with some M double prime when M came to W, and W rejected M because M double prime was more preferable than M, but maybe in the later step M prime came to W and it break off with M double prime and matched with M prime, because M prime is better choice than M double prime for her. Okay. So, this may happen, but in both the cases, like even in this case, M prime is more preferable than M double prime, right. So, basically we can say that M is definitely less preferred than the current matched partner. Okay. But and if it is so, then that means this matching is a stable matching, right. So, that means this implies M W is, this pair is stable, right. So, which is a contradiction. Okay. So, this is the case. Okay, we have two cases. This is case 1 when M proposed W. What if what if M has not proposed W? and that is why they are not matched. Can it happen? That
W prime is more preferred than W, because M would have proposed to W prime accepted, so that is the reason why M did not propose to W.
yes, exactly. So that means W prime is more preferred than W, because then only M goes to W prime first, and in that case, because W prime is more preferable for M than W, so this is again a stable pair. Okay. So that means we got a stable matching. Is it okay for everyone there?
Yes.
Okay. Yeah, so that's all we had. It is easy, right? That proof was like very like their terminology was very difficult to understand, but this one is easier. Okay, so because we have time, so we can just look at some corollary, like which I couldn't discuss earlier. So what we discussed, we gave a characterization for one factor in general graph, right? What was that? Okay, let's I'll just let's look at some application of like Tutt's theorem. Okay. So, we will prove that every bridgeless cubic graph has one factor. So, we saw that Tutt's condition, that is necessary and sufficient to for a graph to have one factor, right. So, to prove that this graph has one factor, we need to show that it holds Tutt's condition hold for every subset of vertex set. That is our goal, right. And by the way, what is cubic graph? Cubic graph is when for every vertex V in V, degree of V is exactly 3. Okay. This is cubic graph. And what is bridgeless? Do you remember bridges?
There are no edges such that if you remove it,
Yeah, it gets disconnected, right, or number of connected components increase. Okay. So, it has no such edge, no bridges. Okay. So, what we need to show that every for any set okay. So, basically this is the goal. Okay. So, this is my S, these are my odd components, okay. And I want to check this number that for any set this holds. So, we will start with any subset of Vg, and for this we will try to prove this condition. Okay. Okay, so First of all, let's look at the number of edges going from S to G minus S. Okay. So, what is that number? Number of edges going from S to G minus S. So, how many edges will be going there? We know that our graph is cubic, bridgeless. Can you give me any lower bound? So, we want to count the number of edges? Yeah, that is true, but better upper bound, like more general. 2 is true, but like, yeah. Look at the degree.
Only one edge between a component and S, then that will be a bridge.
Yes.
At least 2 times the number of components, connected components.
Yes, good. So, at least 2 times number of components, odd even any, right? Okay, number of components, or let us say Cg minus S. We defined earlier Cg minus is the collection of all components in G minus S. Okay. This is one bound. Anything else? So, let's look at the degree. We know that this is a cubic graph, right? So, from okay to Cg minus S, yeah, that's right. So, this is even better bound what you are giving.
But the problem is bridgeless cubic graph can already be disconnected.
Bridgeless cubic
Graph can be disconnected also, because the bridge is an edge which increases the number of
yeah, exactly.
So this one will be correct.
Yes, true. Yeah, so may not be every component, but whichever like is connected to S. Okay.
In that case, we cannot even say it is greater than equal to 2, right?
Hmm?
In that case, we cannot even say that it is greater than or equal to 2, right? Because
No, we still can say 2, because if you have only one, then you can remove that edge. That is a bridge basically. If you have only one, then that is a bridge.
no, it could be 0, right? I mean, S could be independent. We don't know whether G is connected or not. Is G connected? S could be a single connected.
Okay. Interesting. Okay, let's say that it is connected.
So why is the previous bound incorrect?
Hmm?
At least 2 times the number of components.
What?
Why is the previous bound incorrect? At least 2 times the number of components.
Because maybe there are some components which are already there, like separately. If it,
Assuming G is connected.
yeah, if we are connecting, if we are assuming, then it is okay. So, okay, we may assume that it is connected, because anyway in able to have a one factor, for every connected component we need to find one factor. Okay, so the problem again comes up with that every connected component has one factor. So, let us assume, and that is also cubic, bridgeless, right. So, that also satisfies this bridgeless, cubic, and again we want to look at one factor. So, let us assume that this is connected. Okay. Okay, let's what about upper bound?
Degree and not continuity of S.
Hmm?
3 into cardinality of S.
Yes.
In a 2 into because S itself is connected within it. So one edge should be used within.
It's okay, maybe S is 1 itself, maybe cardinality of S is 1, and we are taking upper bound, so this is also fine, right?
This one.
This is correct. 2 we cannot say, like maybe for not for everybody, then we have to say okay, S is not more than cardinality 1. Okay. Yeah. Okay, so upper bound we got 3 into cardinality S. For lower bound, what you said, that is like 2 into cardinality of Cg minus S. Okay. So this is like some upper bound on this. So by taking these two, basically what we have, if इसको कुछ बोल देते हैं, like say this is Z cardinality of E prime. Okay, so cardinality of E prime is at most 3 cardinality of S, and this you have suggested, right? What we want to prove? We want to prove this, right? So let's remove this and put something else. We just want to look at the odd components. Okay, we are not worried about the Cg minus S. So basically, we want to replace this with some C into Qg minus S, and what this C is, what this 2 was, that how many number of edges at least going from any component to S. So basically this C can be the number of edges going from S to some odd component. So we want some lower bound, some odd component. Okay. So 2 is still okay, because this graph is bridgeless, so 2 is okay, but still we will look for better bound. Yeah, for better one. So we have at least 2. Yeah.
It's not yet clear to me why the lower bound is 2 Cg minus S.
2 Cg minus S, because okay, so this is S, this is my any component written it. So can we have only one edge from S to this component?
One is,
From S to some component.
yeah.
We cannot have, right? Because this will be a bridge otherwise. This is a bridge.
Oh yeah, that's right.
Yes, so that's why at least 2 edges should be there between S and any component. So that's why 2 into Cg minus S, because I want to achieve this inequality, so I'll look at the number of odd components only. Okay, so I'm saying that okay, 2 into number of odd components, at least these many edges will be there. This is still fine. So we see, if I put C is 2, then it is fine, but still it won't give me this inequality. So what I want to prove is that can we have some better bound than this. Okay. Okay, so for C is equal to 2 is already there, but we want to improve this too.
I have a doubt. So let's assume the size of S is greater than 1. So in that case, the E dash is less than or equal to 2 into S for sure, right?
If
Size of S is greater than 1.
size of S is greater than,
Because within S, everything should be connected.
Not necessarily, right? It could be an independent set also.
Yeah, overall graph should be connected, right? But S, it may have something like this, and I can just choose this S. S is any subset of vertex. So we can't improve this one, and okay, we are happy that we have at least cardinality of S in terms of cardinality of S, some upper bound. Let's look at this side, because we want to replace the Cg minus S to Qg minus S. So let's look at some odd component and try to see what happens. Okay. Okay, so we have our S, some odd component, say C. Okay, so it's not clear. Let C be an odd component. Okay. So this is odd component, and this is a cubic graph, right? So if we want to look at that how many edges are going across this bound, we need, right, a lower bound on this edges. Okay. So let's what can we do? We can just look at the degree sum here, basically the number of edges inside C, and okay, but because C can have some edges going outside as well. So let's look at the degree sum. So let's look at the degree sum for all the vertices in C, in G. It will be odd, because what is it? Every vertex has degree exactly 3. So 3 times how much? Cardinality of C, because every vertex has degree exactly equal to 3, and total number of vertices cardinality of C. Now this is also odd, right? So this means this degree sum is odd. Okay. Now basically this degree sum is what? We have number of edges, but some of the edges are counted twice, right? Which edges are counted twice? Which are inside, because you are looking at the degree of both endpoints, but for these edges we are looking at the degree of only one vertex, because one of the endpoint is in S. Okay. So basically to count these number of edges, we can just from the total degree sum we can just remove the degree sum here from the component only, and then after subtracting these we can just get the number of edges going across from this component. Okay. So that's my idea. So what we want to look at? The degree sum inside C. So for the timing, suppose we don't have these edges, we have this component only. So inside this component, now look at the degree of each vertex in the component C. Now there are some vertices which has degree not equal to 3. Okay. These vertices have lower degrees now, so we don't know that. But so degree is not now 3 into cardinality C is not there, but still can we say something about it, that what would be this degree sum inside C, and now we are looking at the new degrees once we remove these edges.
The degree sum will be even.
Yes, this will be even, because degree sum of a graph is like twice of number of edges, because every edge is counted twice in the degrees of the endpoints, right. So, this will be twice of S set of C, and so this is even, right. Now, what is the number
The
of,
number of edges between the component and S will be odd, but it cannot be 1 and it cannot be more than 3. So
it will be at least 3.
No, but that would be edges from C to some other component which is not S, right?
But I have C we got after removing S. So, why C will have edges to other components? S has edges only to C, right. We have removed C, then we got C. We have removed S, then we got C.
No, but I mean, while considering no, this 3 into C that constitute, I mean, that had edges which were part of other connected this connected component and other connected components as well, right?
Not other connected component in S, because it can have edges only in S outside C.
How?
Because you had some graph G, we chose some S, and after removing S we got this C.
Okay, yeah, got
So, you have edges only between S and C. Okay. So, what we say that V belongs to C, degree sum is equal to degree sum here inside V plus what are the other degrees, is the number of edges between S and C, right. And now, this is odd, this is even. So, what we got, that number of edges S to C is odd, right. And now, it can't be 1, we already said that, because the graph is bridgeless. So, this is at least 3. So, we got a lower bound on this. So, if what I wanted, we had C into Q G minus S three cardinality of S. What we got for C, at least 3. So, we got some lower bound here, and so Q G minus S is at most cardinality of S. That is all. That is we wanted to prove. Okay. So, we are done. We proved the Tutt's condition. Is this proof okay for everyone?
I have one question.
Yes.
So like, is this thing like tight? Like tight in the sense like if suppose there is a cubic graph which contains exactly one page, then will it have a perfect match? Or like if it has 2 pages?
I don't know, like you have to think about it, whether it is like tight or not. Right now, we can't see that it is tight.
Yeah, but I saw a proof like using this Tutt's theorem and there's a Tutt-Bunch formula. So it gives a bound on like if a cubic graph can have like has number of pages at most 2, then it also has a perfect match.
Okay.
It also uses this Tutt's theorem. That's why.
Okay. No, but in that case, like we won't be able to argue that this is like at least 3, because now you are allowing to have 2 bridges. So,
Yeah. In that case, like we need this Tutt-Bunch formula.
yeah. So, yeah, a different proof we require, like the same way we cannot prove. Anything else? Otherwise, I think we are done. Okay, it's good.